Good morning. I'm Chris Koeppen, Chief Technology Officer of 26 Incorporated. And the title of my talk today is Light Matters, Photons, Photons Everywhere. Now, before I begin, I'd like to again welcome everyone to the 2020 IEEE Photonics Conference. And I'd also like to thank the organizing committee, the IEEE Photonics Society, and to all of those who have contributed to and are participating in this week's exciting and invaluable program. And I'd also like to thank you who are watching and supporting this conference. Now, when I was asked to give one of the plenaries, I reflected on what might be complementary to the amazing technical research and advances being presented this week. Coming from industry, I thought it would be interesting to highlight the tremendous growth of photonics and its applications across an ever-increasing number of markets. The breadth and depth of the impact that photonics has had and will continue to have on the world that we live in is truly incredible. Now, at the heart of these photonic applications are the underlying materials. For those of you that know 26, and for the benefit of those of you who do not, as you might guess, our name comes from the periodic table. We were founded in 1971 to leverage elements from columns 2 and 6, namely cadmium telluride and zinc selenide, to make high-performance optics for CO2 lasers. Now, in order for CO2 lasers to be commercially viable for industrial materials processing applications, we had to carefully engineer the crystal materials for low absorption. Otherwise, the optics would have burned out way too quickly. So the interactions of light and matter and advances in the materials that underpin them are critically important for the growth of our photonics industry. But where to start? Well, let's start at the beginning. Light has been integral since the origins of the universe and the formation of the Earth. The inception and evolution of life has depended on photons from the sun, with photosynthesis playing a central role. The conversion of light energy into chemical energy through photosynthesis supplies most of the energy necessary for sustaining life on Earth, with an average rate of energy capture on the order of 100 terawatts. Now that's about 10 times the power consumption of human civilization. The efficiency of converting sunlight to stored energy through photosynthesis is a few percent, and we will find this type of efficiency to be a recurring theme in viable applications of photonics. Namely, that it's the efficiency of the underlying light-matter interaction that is important. In moving from light being used for sustenance to light being utilized for observations, science, and the acquisition of knowledge, the collection efficiency of light, first through human vision and then through engineered glass and lenses, became important. Early astronomy led to our understanding that the Earth was not the center of the universe, a foundational moment for science, thanks to the development of optics for telescopes. More than for just observations, light became used for functional purposes, such as navigation and communication. For example, lighthouses serve both purposes by providing an intense beacon of light to signal their whereabouts, and by modulating the beam to communicate their identity and other basic information, an early form of on-off keying. Here again, innovations in engineered materials, this time through the invention of the Fresnel lens, enabled the distance to be increased substantially to over 20 miles, 5 times farther than with standard reflectors. These lighthouse signals were one of the first implementations of long-distance optical communications. It's also interesting to think about how far we've come in terms of energy per bit communicated. If we consider this lighthouse example, with a light on the order of 1,000 watts operating at about a hertz, that would result in a kilojoule per bit transmitted. Now let's contrast that with today's high-speed optical interconnects, which can operate down to 10 picojoules per bit and even trending toward 1 picojoule per bit. That's an amazing 14 to 15 orders of magnitude improvement, primarily through innovations in photonic materials. Now, as science began to understand the interactions of light and matter and their importance, there have been a number of seminal inventions. One of the wonders of light is its wave-particle duality and the associated ability to exchange energy with matter in either direction. Einstein's formulation and explanation of the photoelectric effect in 1905 described quanta of light energy, aka photons, being transferred to electrons. It was the work for which he eventually received the Nobel Prize. The photoelectric effect and related discoveries in the early part of the 20th century marked the beginning of the existing era of photonics. Now, of course, the transfer of energy from photons to electrons can be reversed when electrons in higher energy states transition to lower energy states, generating photons. As we know, this reverse principle led to the development of light amplification through stimulated emission and the invention of the ruby laser in 1960, which was followed soon after by the invention of the gallium arsenide semiconductor laser in 1962. Coming back to the theme of efficiency, we need to consider quantum efficiency, which is the ratio of conversion of energetic electrons to photons and vice versa. The power conversion efficiency of a laser is directly related to its quantum efficiency, which in turn relies heavily on the quality of the underlying materials and device interface layers. When considering some common examples, a helium neon laser has an efficiency of only about 0.1%, and CO2 lasers have efficiencies in the range of 10 to 20%. Now, in contrast, through significant developments in semiconductor materials and associated processes, gallium arsenide lasers have reached efficiencies in excess of 70%. Now, such high efficiencies have enabled commercial applications that would otherwise not be viable, including those that are operated by battery power, for example, such as your phone. Now, another common example or everyday example of an application that uses the same efficient semiconductor materials is LED lighting. Now, LED lights have efficiencies of 40 to 50%, which is 10 times higher than the incandescent sources they replaced. So one thing I can say is if the photoelectric effect marked the beginning of the era of photonics, it is the laser that marked the foundation for the growth of our industry. It is truly exciting for us to be part of this vibrant photonics industry, which is driving so many global megatrends. Here we can see the growth in global laser sales over the 50 years following the period of the first commercialization of lasers. Now, while the photonics market is certainly significantly much higher than just the laser market, we find laser sales are a very good proxy for the growth of the overall industry. We can see that since the mid-1960s, leading up through 2015, the market has grown over 1,000-fold at a compound annual growth rate of 15%. That's an amazingly high sustained growth rate over a 50-year period. Now you can also see some features in the chart that are reflective of the global economy. First, you can see the acceleration of the optical communications growth prior to the 2000 peak and subsequent fall off when the telecom bubble burst. Then we can see the recovery and the increase in the global economy prior to the financial crisis of 2008. The tracking of the laser industry and the overall global photonics industry to the world economy is really indicative of how economic output and the photonics industry are now closely intertwined. Now that we've reviewed the historical growth, let's take a look at growth over the next 5 years by different market segments. Again, we can consider the growth of lasers as a good proxy for the growth of the photonics industry as a whole. Now, just looking at the number of markets shown, which is not even a comprehensive list, we can see how ubiquitous is the application of lasers and photonics. With some of the earliest commercial applications, Currently, the largest market for lasers is industrial materials processing, growing steadily from over $5 billion this year to around $6.5 billion in 2025. This is followed closely by optical communications, which is expected to strongly increase by almost 60% over the next 5 years. Moving clockwise in the picture, aerospace and defense will nearly triple as national defense and satellite systems begin to more fully leverage laser technology. Photonics-based sensors and instrumentation for both consumer electronics and automotive are now becoming pervasive as well. Strong growth is similarly expected in semiconductor equipment, including photolithography, as well as in life science and healthcare applications. In total, the compound annual growth rate through 2025 is projected to be a robust 10%. If you want more evidence of the wide spectrum of applications, just consider the talks being presented this week. Let me read a few. Photonic beamforming for communication satellites. The guided mode resonance biosensor. Embedded photonics for deeply disaggregated computing systems. Stretchable displays, electronics. Diffractive liquid crystal devices for AR/VR displays. Optical coherence tomography for use in infrared laser sealing of blood vessels. And of course, the preceding plenary from Professor Chang Hasnain on VCSEL arrays for 3D sensing. So many interesting applications. Now, I'm sure most of you are here for a particular application or market, but I'd ask you to attend a talk in a different area that you might not have otherwise attended. I'm sure you're going to find it both fascinating and inspiring. Okay, so let's now take a look at the largest market for lasers. For industrial material processing, laser light serves as the basis of many tools that we use to transform a surprising array of materials that find their way into many products that we buy. CO2 lasers emitting at 10 microns were one of the first widely deployed for materials processing, as they could be operated at high power and were effective at cutting steel. However, advances in engineered materials for optimized efficiency, namely with gallium arsenide semiconductor lasers and rare earth doped fibers, have enabled fiber lasers operating at a more highly absorbed 1 micron to disrupt CO2 lasers in most metal processing applications. Nevertheless, with their 10 micron wavelength, CO2 lasers continue to have significant applications for polymers and organic materials. For example, they may have cut the treads in your shoes or been used to fade your favorite jeans, as shown in the upper left inset picture. The inset below the jeans displays a green laser cutting super hard polycrystalline diamond. As you may guess, lasers are often selected based on the wavelengths of the absorption peaks in the materials that they process. Additional recent and emerging applications leverage ultra-fast high peak power lasers for fine feature cutting and precision ablation. With careful selection of wavelength and precise control of beam profile and dwell time, certain intricate and multi-component parts can be additively manufactured using less material and in less time, and at the necessary quality and reliability. Some common examples are based on lightweight alloys used for jet turbines, rocket fuselages, and manifolds in racing cars. Other emerging applications previously exclusive to mechanical or other means include grinding, lapping, or even cleaning, where laser light is swept across a surface as shown in the following video, where a thin layer of material is lapped away from a polycrystalline diamond disc. As you can see, there are almost a countless number of applications. Now, one industry in particular that has been transformed by laser processing is automobile manufacturing. Whether you are in a Tesla plant in the US or an Audi plant in Germany, you will see lasers mounted to robots everywhere. Laser welding is now common practice for all standard vehicles, It's used in the body frame construction and stiffening, for doors and enclosures, and in complicated welds for the seating, including the front seat frames and the recliners and tracks. It's also used to weld the roof to the body and can actually make very precise weld joints that are ready to paint, which reduces overall touch time for the vehicle. Laser welding becomes even more important for electric vehicles. In addition to the major frame and assemblies, laser welding is critical to the electric motor as well as multiple process steps for the battery. In optimizing vehicle weight and electric operation, aluminum and copper are employed more prevalently in combination with steel. Accordingly, different laser wavelengths and pulse profiles are necessary based on the specific material absorption and weldability, including welds having combinations of materials. The setup also requires a high degree of flexibility in going from high power welds for the body frame to fine precision welds of the battery seals and electrodes. After industrial materials processing, optical communications is the second largest market for lasers and is growing rapidly. While the size of this market is about $3.5 billion, the total optical networking equipment market is around $16 to $17 billion, and there is no end in sight to the bandwidth demands that are driving its growth. Consider that a 16K TV needs around 6 gigabits per second of compressed bandwidth, certainly more than most networks to the house can handle. But a full parallax high-definition holographic display will need more than 10 terabits per second, over a 1,000-fold increase. Then when you layer on artificial intelligence and machine learning to analyze such holographic images, you can expect an unending bandwidth demand for the foreseeable future. Now, I have spent the bulk of my career over the past 2 decades in the optical communications industry, and I can't think of a better example or a more fertile ground for innovations that leverage light-matter interactions and have relied on the significant advances of the underlying materials. Let's take a look at a few examples. Setting the stage for optical communications was the pioneering work on the transmission of light in optical fiber by Charles Kao in the 1960s, for which he received the 2009 Nobel Prize. The promise of fiber optic communications eventually led to one of the most efficient and successful waveguides in history, with optical fibers achieving less than 1/4 of a dB of loss per kilometer. Leveraging such low loss, signals could be transmitted on the order of 100 kilometers, much farther and with much less required power than our earlier lighthouse example. Now, in order to transmit longer distances without expensive optical to electrical back to optical conversion, another materials-driven invention came to the rescue, the erbium-doped fiber amplifier. Compliments of David Payne and his team at the University of Southampton in the 1980s. Properly designed, these optical amplifiers have gain across a relatively broad spectrum around 1550 nanometers. So when it became too expensive to increase the modulation rate of lasers and receivers, wavelength division multiplexing, aka WDM, was developed to transmit multiple wavelengths over the same fiber. Yet again, more materials-based innovations were required to enable WDM networks. For one, the transmit laser center wavelengths needed to be carefully controlled, and so periodic refractive index profiles interacting with the diode laser cavities were introduced to lock the diodes to specific wavelengths. Additionally, thin film filters with many layered dielectric stacks were developed to select one wavelength out of the set of many wavelengths. Tens of thousands of hours of careful materials engineering went into these types of devices to balance stresses, reduce defects, and improve yields to commercially viable levels. Now, once multiple wavelengths were on a fiber, additional inventions were required. Large effective core diameter fibers with carefully engineered dispersion profiles were necessary to mitigate the deleterious nonlinear effects of optical interactions such as four-wave mixing between the channels and the fused silica core. There also became the need to monitor the powers of the individual wavelengths. The most prevalent technology for this optical channel monitoring today is based on a thermally tunable multi-layer stack of amorphous silicon and silicon nitride that lets specific wavelengths reach a detector based on the tuning of the stack temperature. Wavelength selective switches were also developed, employing liquid crystals to switch and attenuate wavelengths and to optically route individual channels to different fibers by leveraging diffraction and polarization. More recently, coherent transmission techniques have been employed to transmit 800 gigabit per second channels over many hundreds of kilometers. Relying on both precise optical phase and polarization control, coherent modules have driven the development of narrow linewidth tunable lasers and the photonic integration of multiple functions into indium phosphide and silicon photonic chips. These are truly incredible displays of material innovations to enable photonic functions. So what does the future hold for optical communications? Well, as processors, accelerators, and memory get faster and faster, and with architectures such as for high-performance computing, artificial intelligence, and machine learning driving more interconnections between them, the electrical interfaces are becoming limiting in terms of distance and power. Longer reach, high-speed transmission is a strength of optical communications, and so optical interconnect technologies are being developed for chip-to-chip data transfer. Innovations in photonic semiconductor devices, such as high-speed gallium arsenide vertical cavity surface emitting lasers, aka VCSELs, are enabling directly modulated parallel interconnects over multimode fiber. For example, the hybrid integrated chip shown in the upper right comprises 16 VCSELs operating at 56 gigabits per second for a total chip-to-chip bandwidth of 900 gigabits per second. Similarly, indium phosphide and silicon photonic integrated circuits are enabling multiple WDM wavelengths to be transmitted on individual single-mode fibers for chip-to-chip interconnection. With 16 wavelengths per fiber, and each wavelength operating at 25 gigabit per second over 8 parallel fibers, the upper left picture shows 3.2 terabit per second transceiver chiplets for switch-to-switch interconnection. Now, as photonics moves closer to the ICs, optical interconnect technology needs to be manufactured with processes compatible with those of standard semiconductor assembly and test in order to achieve the necessary cost, quality, and scalability requirements. As an example, let's take a quick look at a video showing the automated assembly of both optical and electrical ICs into an integrated multi-chip assembly. Moving on to aerospace and defense, we can see that this market significantly leverages photonic technology platforms and products from industrial materials processing and optical communications, but adapted to its unique requirements and challenges. In addition to some of the more commonly known photonic applications like optical surveillance, laser targeting, and night vision, significant recent investments have been made in satellite laser communications and high-energy laser beam combining. These investments are being made in both the commercial and defense sectors. For example, SpaceX has announced Starlink, which will be a constellation of many thousands of satellites in low Earth orbit that will deliver broadband internet access across the globe. Satellite-to-satellite communication in Starlink will be through free space optical laser communication links that likely will leverage the high-speed coherent transmission technologies mentioned earlier. As for the high-energy laser programs receiving significant defense funding, they similarly leverage the high-power fiber laser technology for materials processing. For example, the high-energy laser beam combining system shown here coherently combines multiple high-power fiber lasers in order to deliver the combined power to a remote target miles away through tough atmospheric conditions. This laser beam combining system also provides promise as a phased array energy source for future space exploration programs like Breakthrough Starshot, as featured in National Geographic. Theoretical physicist Professor Stephen Hawking and science philanthropist Yuri Milner unveiled the Breakthrough Starshot initiative in 2016 to send laser-propelled space nanocrafts toward Alpha Centauri, the closest planetary system to ours. These nanocrafts would fly at 20% of the speed of light and capture images of possible planets and other scientific data in the Alpha Centauri system just over 20 years after their launch. Of course, many more materials innovations will be necessary to realize such a vision, but the promise of photonics is certainly unbounded. Speaking of unbounded, the potential number of applications for photonic sensing in consumer electronics, industrial automation, and autonomous vehicles is mind-boggling. Full 3D positional mapping and awareness opens up countless opportunities in our everyday lives, with just a few listed here. In November 2017, the iPhone X was released into the market, ushering in a new era for photonics-based 3D sensing in consumer electronics. Employing a gallium arsenide VCSEL array, the iPhone X uses facial biometrics through structured light mapping and analysis to unlock the phone. VCSELs are also used to help detect when someone holds the phone up to their head, or insert AirPods in their ear for that matter. Since that introduction, 3D sensing has been adapted in tablets and is becoming more common in laptops. This year, we may also see smartphones adopting world-facing, time-of-flight-based 3D sensors on the backside of phones for augmented reality and other advanced camera features. With over 3 billion smartphone users globally, the market penetration and associated use cases are still in their infancy. Augmented reality and virtual reality, AR/VR, are enabled by photonics through both 3D sensing of the environment and the sophisticated optical projection of the constructed image to the retina. More than just the next generation of gaming, AR/VR promises to transform the educational, training, and remote presence industries, among many others. By combining AR/VR with spatially aware robotics, high-value applications like remote surgery, equipment diagnosis and repair, and unfriendly environment exploration are becoming a reality. Even household toys and appliances are beginning to leverage 3D sensing technologies to enhance our everyday lives and increase productivity. Speaking of convenience, Amazon and others are already testing delivery services using drones and mobile robots equipped with depth and spatial sensing to arrive at our doorstep soon after we click purchase. More than just important for consumers, 3D sensing is crucial to revolutionizing factory automation with machine vision for Industry 4.0 and beyond. As with the other markets, here again we see materials and light matter interactions underpinning photonics technology. In the case of 3D sensing for smartphones, gallium arsenide semiconductor VCSEL arrays provide the source illumination. But why use VCSEL arrays, and what materials challenges were required to be overcome? A primary benefit of VCSELs is that their laser cavities are vertical, with emission perpendicular to the semiconductor wafer surface. In manufacturing, this geometry enables wafer-level inspection and testing, which is an absolute necessity to meet the throughput and cost requirements of such a high-value application. Additionally, 2D arrays can be made to scale the power or control the spatial distribution of laser light. For the smartphone application in particular, thickness is also a critical dimension, again playing to the strength of a VCSEL with its geometry of just a few hundred microns thick. But what challenges in the materials were required to make these VCSEL arrays a commercial reality? First of all, with a thin quantum well gain region, many passes are necessary to achieve sufficient output intensity. This requires high reflectivity distributed Bragg reflectors with many epitaxial layers. Precise sub-nanometer level control of many tens of high-quality epitaxial layers is exceedingly difficult. Also, defects or impurities can lead to degraded performance and long-term reliability issues. Introducing dopants such as aluminum and indium to gallium arsenide for the different refractivity layers creates significant mechanical stresses that need to be managed across the array as well as over operating temperature. And these challenges become exponentially more difficult in moving to 150 millimeter diameter wafers, which were necessary to achieve the required commercial scale and costs. So you can see how VCSELs are yet another beautiful example of the marriage between material science and photonics. Another large and fertile market for sensing is automotive, particularly in the area of advanced driver-assisted systems. While we are starting to see some of these features, such as adaptive cruise control, lane assist, and blind spot alert, advanced laser and optical imaging technologies promise to expand them significantly and ultimately toward autonomous vehicles. While photonic semiconductor materials are not new in automotive, with the high power conversion efficiency of LEDs on their way to replacing conventional halogen or xenon headlights, lasers are enabling new functionality. By now, everyone is quite familiar with the promise of LiDAR to map the 3D terrain in front of and around the automobile. Multiple different LiDAR technologies are being developed, again leveraging the foundations from industrial materials processing and optical communications. These range from edge-emitting multi-junction pulsed gallium arsenide lasers at 905 nanometers to frequency-modulated continuous wave indium phosphide lasers operating at 1550 nanometers. On the receive side, multi-layer dielectric stack filters with wide acceptance angles were invented to filter out background light over the required wide viewing range. Ultimately, multiple technologies, including thermal imaging, may be used in tandem depending on the distance and resolution necessary for specific features. Now inside the car, in-cabin sensing, predominantly with VCSEL technology, will be used for driver and passenger gesture recognition and monitoring. Advanced heads-up and future holographic displays will also be enabled by photonic and material innovations. Now, if there were an award for the most light matter innovations in a single piece of equipment, the extreme ultraviolet EUV photolithography equipment by ASML, with the support of its many partners, would be at the top of the list. Before we dive into these innovations, let's first consider the tremendous impact that this application of photonics, namely photolithography, has had. Photolithography enables the patterning and production of all the sophisticated integrated circuits driving our smartphones, computers, internet connectivity, cars, appliances, and pretty much every aspect of our everyday lives. The miniaturization of electronics and continuation of Moore's law relies on photolithography technology, which operates at the frontier of the diffraction limit of light. At the cutting edge in photolithography today is EUV, which enables semiconductor features as small as 7 nanometers and going down to 5 nanometers and even lower in the future. The wavelength of the EUV light is 13.5 nanometers, bordering on the X-ray band. So how is EUV light created? That brings us back to the innovations I mentioned earlier. It's an amazing combination of technology and engineering in which high-power 10-micron CO2 laser pulses strike tin droplets, creating plasma that emits the 13.5 nanometer light. In fact, it's two pulses, a pre-pulse that hits the droplet and causes it to swell into a disc-like shape for increased cross-section, and then the main pulse that gets absorbed to form the plasma that generates the EUV light. quite an incredible example of light-matter interactions. With billions of dollars invested in R&D, these EUV machines, at a price tag of over $100 million per system, incorporate many other photonic innovations, such as heat dissipative CVD diamond windows for separating the different laser compartments, and cadmium telluride modulators for temporally shaping of the 10-micron pulses. Also, consider the optics by Zeiss to shape and direct the EUV light. It's one thing to specify the surface quality to lambda over 10 when the wavelength is 632 nanometers, but quite another when it's 13.5 nanometers. In fact, the mirrors are made with a surface roughness of 0.1 nanometers, which is about the diameter of a hydrogen atom. While we can talk about many more technological feats, I think it's safe to say that EUV photolithography is a quintessential application of photonics. Now, let's turn our attention to a market and industry that has come to the forefront this year with the COVID-19 pandemic. Photonics is increasingly finding its way into analytical instruments for biotechnology, medical, and life sciences applications. Biological molecules and processes can leave identifiable fingerprints through excitation with appropriate wavelengths of light, either intrinsically or in combination with fluorescing biomarkers. These molecule-light interactions have enabled DNA gene sequencing to become commonplace and with high throughput. Optical coherence tomography leverages tunable light sources and spectrometers along with coherent techniques to construct high-resolution maps of the retina, blood vessels, and other biological features. Photonics also promises to be at the core of next-generation biosensors, combining photonic integrated circuits with laser diodes and spectral detection at targeted wavelengths. Now returning to our current situation with COVID-19, photonic biomarker identification enables the polymerase chain reaction, PCR, instruments at the front lines of patient testing and diagnosis. Accordingly, photonics is critically important to our fight against COVID-19 and future pandemics. As I'm sure you will agree, with so many important applications across almost every industry, our world has been transformed through photonic innovations and the underlying materials that enable them. Now, I expect most of you, like I do, have backgrounds in photonics. So the next time you see one of your materials scientist colleagues, please offer to buy them coffee or lunch to thank them for their tireless pursuit of materials that will lead to your next invention. As I wrap up this talk, you don't have to look any further than the smartphone in your hand to understand how photons make for a better life. Here you can see the convergence of all the market applications we have reviewed. It is connected to the cloud and the world through fiber optics. It employs 3D sensing for biometric identification and augmented reality. It will enable biosensor-based health monitoring. It's fabricated with laser technology, and it's powered by core processors produced with photolithography. I'd like to conclude with II-VI's vision, which I believe aligns well with that of our photonics industry. To enable a world transformed through innovative materials vital to a better life today and the sustainability of future generations. Thank you for your attention, and please enjoy this exciting week of talks.